It is a work of art, an engineering marvel, and a machine built to best an icon.
We only make one car, and then we do that only every 10 years.
Now, France's most famous marque is back with an all-new 2.4 million euro, 1,500 horsepower machine called the Cheron.
If we say we want to build a car that makes it to a top speed above 400 km per hour, you need to deliver.
After nearly a decade of design and engineering, it's finally time to push the boundaries of the automobile.
This one is a pre-production car.
Before the brand can deliver the machine to market, they must first race the clock and crack the 400-kilometer barrier.
Here, have you a look on this? It's such a...
Every day counts, and there is no margin for error. This is a once-a-decade inside look at the last big push to build the next Bugatti. Welcome to Molsheim, France. A land rich with history and the ancestral home of Bugatti automobiles.
We are here in the atelier. That's the place where we produce all the Veyron before, and now we had to adapt the atelier to the new car, to the Cheron.
This is one of the most unusual car factories in the world. Everything here is artisanal, and there's rarely a rush. Yet today, the pressure is palpable. It is just 6 months before the brand's newest hypercar begins production.
We have a short period of time to get going in our factory, so the next race is running.
Just 500 cars will ever be built, and each one carries a 2.4 million euro price tag before options. Yet two figures really stand out. The 1,500 horsepower engine and the goal to beat its predecessor's outright top speed on the racetrack.
At present, we are the holder of the world speed record for supersports cars with 431 km per hour. The new one will be remarkably faster.
It's a laudable target, but before the brand can achieve the goal, they first have to finish developing the machine.
In this phase of the development, we have a lot of stress to bring the knowledge from the prototype to the series car.
What we have to do now is the final tests.
Ensuring that the Cheron works correctly is crucial. There's very little about the machine that is normal. And perhaps no car in modern history has had to bend physics quite so far in order to dethrone what came before it.
We always have physical boundaries based on technical circumstances, but boundaries can be pushed.
In 2005, the brand introduces the Veyron. It is a moonshot, the likes of which has seldom been seen in the automotive world.
Our Veyron customers have all the reasons to believe their car is unbeatable.
10 years later, however, it's a different story. Competitors nip at the company's heels, and the marque needs a new machine to hold on to their record for the world's fastest production car.
The brief basically had one line: do everything remarkably better than in previous time.
When the project begins, the target is clear, but the path is not.
If you start a car project like this, where you really go to the border of physics, if you would know everything right away, then it would be easy. But this is not the case.
The team's first major decision cuts right to the heart of the matter. To hit a new top speed, they need a brand new engine.
There was a lot of speculation in the market, whether it will be an electric car or maybe a hybrid, or will it be a combustion engine supercar again.
Engineers decide that the best course of action is to build upon the Veyron's famed W16 power plant.
The biggest one is the requirement to improve the horsepower.
Upping the ante has been a hallmark of the automotive industry since the beginning. The saga starts in 1886, when German inventor Carl Benz bolts a single-cylinder motor which has less than 1 horsepower onto a 3-wheeled carriage. 2 decades later, in 1908, Henry Ford puts the world on wheels when he introduces the Model T. The machine transforms society with just 22 horsepower. 47 years later, the first production car with a 300 horsepower motor arrives. Yet it will take another half a century before the introduction of the Veyron more than triples the number.
Around the world, you can find a lot of supercars that have strong engines, that are powerful and drive very good. To have a unique design, a piece of automotive art, this is the challenge.
By 2010, the car world is a very different place. At the dawn of the decade, over 50 different production cars now offer more than 400 horsepower. Almost 60 models come standard with 500-plus horsepower engines. And around 20 more machines have motors producing over 600 horsepower. It is the golden era of the combustion engine.
Well, I think competition makes our life a little bit easier. You also can get spirit from your competitor cars.
Where the Veyron once stood all alone, now there are at least 5 different hypercars capable of producing over 800 horsepower and hitting top speeds in excess of 340 kilometers per hour.
The automotive market is the most challenging industry we see around the world. It's highly developed, and there are thousands of creative guys thinking about new technical solutions.
The Cheron is perhaps the last, best hypercar of its era. And the zenith of the internal combustion age.
It's the last real combustion engine in this horsepower level, because it's very complicated to make 1,500 horsepower as a combustion engine in such a car.
The man pushing the limits of combustion tech is Wolfgang Dürheimer, the CEO of the brand.
Started all on motorcycles. I was probably 11 or 12 years old, and I saw these guys racing and jumping, and I decided this is what I'm going to do when I'm a little bit older.
Dürheimer quickly realizes that his gift isn't piloting a machine, but rather designing it.
I can practice day and night. I never will be a world champion. So I thought it's better for me to focus on the technological side.
The desire to become an engineer leads him to Munich's Technical University, where he wins a Fulbright scholarship. Yet it's an idle flip through a motorcycle magazine that changes his life.
I read about a problem with racing motorcycles, and I thought this is a good subject to work on.
It's the start of a remarkable engineering odyssey.
I got a call from Porsche. Do you want to become the product line director for the 911?
A year and a half after landing the job, Dürheimer is running Porsche's entire R&D department.
Honestly, at the beginning, I couldn't believe it. I thought that this is the max you can reach as an engineer. It's fast, it's the 911, and you think there is no possibility to peak it again.
One phone call later, that sentiment changes when Dürheimer is offered the top job at Bugatti.
I would say it's a sequence of lucky questions. thinking about the Bugatti offer and knowing this car, you again realize there is always room for improvement.
Improvement that starts 3 years earlier. The last iteration of the W16 produces 1,200 horsepower. To exceed the Veyron's top speed, engineers calculate that a new engine needs a 25% increase in power. That's equal to the entire motor in a normal car.
We defined very early in the project that we need 1,500 horsepower.
1,500 horsepower motor would be the most powerful engine ever built for a series production car.
Kostet sehr viel Zeit, diesen Motor zu entwickeln. Das kann man in Stunden gar nicht ausdrücken, auch nicht in Tagen oder Wochen. Es sind Jahre, es sind Mannjahre. Wir haben ein Team, das nonstop daran gearbeitet hat, ungefähr 3 Jahre lang.
The power plant takes a long time to engineer, but only 6 days to actually put together. "95% of the power plant is new, but it's the 4 turbochargers that are the key. When the engine is first fired up, only 2 of the 4 turbos kick in. But once the engine hits 3,800 revolutions per minute, the other pair spin into action. The result is an engine that produces maximum torque over 70% of the power range.
Es gab durchaus Probleme bei der Entwicklung, die mich auch nachts nicht losgelassen haben.
The extra power creates another challenge, namely how to cool the new motor. So the team develops a new water pump that's capable of circulating 800 liters of coolant. That's close to 10 average bathtubs. And at full speed, the pump moves that much liquid through the entire engine every single minute. Once the prototype engine is complete, they take it to an advanced test bench, where they discover yet another roadblock.
When we put the engine at first on one dyno, the dyno was overheated and it breaks.
To check their creation, the team has to build a new facility. To prove the engine's metal, they run it for 25 hours straight at full throttle. Were it on the road, the power plant would have traveled from Wolfsburg, Germany to Phoenix, Arizona.
Heat management is a big challenge for such a car. If you have a combustion engine with 1,500 horsepower, you have more than 3,000 horsepower as heat reaction.
3,000 horsepower is enough energy to run an average house for over 2 months. Finding a way to dissipate it comes down to the stroke of a pen and a cut-off line. Team Bugatti has just settled on a preferred engine configuration for their newest supercar. The question they now face is how to wrap it in a beautiful exterior.
A new and next Bugatti is not done like that, with a finger snip. It occupied me day and night. Obviously, in a designer's head is, what's next?
Achim Anscheit is the man tasked with reshaping an icon and keeping a brand alive.
I worked on this car for more than 10 years, and there were various proposals that I did here in the studios. Hundreds of sketches and models that we did. It was a big part of my life. It was a big gamble on my career as well.
Achim's path to a pen doesn't begin with art, but rather an education in the pits.
International field of track motorcycle racers gets off to a fast start.
My personal theory is that you come to car design from 2 ways. Either your parents are architects, designers, or artists in the broader sense. Or you come with a motor virus. My father was a motorcycle racer in the 60s. I grew up in the pit lanes of the Grand Prix world.
Most car design is intended to help sell the machine. Inside the Bugatti design studio, the focus is a bit different. It has to be when you're defining a machine intended to blast well past the 400-kilometer-an-hour barrier.
Everything starts with a lot of thinking, but the thoughts are best expressed by sketch work.
Once the team defines the car on paper, it's time to move it into the digital world.
So I think we started with the negative flicks, right?
Eventually, you still need to touch and feel the machine. So an artisan sculptor creates a full-size clay model. Each panel is lovingly and painstakingly worked until it's perfect. The artistic lines need to look good, but it's the path air travels around the machine that's critical.
For a car to go over 400 kilometers an hour, you need to carefully consider the aerodynamic flow around and through the car.
Funneling clean air sounds easy, but it's not. As a vehicle is pushed forward, it creates turbulence. The more unsettled the air becomes, the less energy it contains. And the W16 power plant needs a massive amount of high-energy air. So, the team turns to Dallara, one of the most famous names in motorsports. If you've ever watched the Indy 500, you've seen their aerodynamically tuned chassis in action.
Here we are in the Dallara's wind tunnel, where we test a 40% scale model, trying and understanding the aerodynamic behavior of the car.
The engineering firm starts in 1972, and their early racing success crystallizes the notion that they can harness the wind.
The wind tunnel has a fan which produces over 1,000 horsepower. This pushes the air towards the model.
Dallara's tunnel can generate wind speeds up to 200 kilometers per hour. It's a far cry from the Cheron's eventual top speed, but fast enough to determine where the cleanest air lives.
Inside the model, we have a balance which measures the forces. And we have up to 250 pressure channels that we use to acquire the data.
The relatively tiny scale model helps aerodynamicists measure airflow around the car and even inside it.
It's difficult to keep a car on the road when you go above 400 km per hour. Just compare that an Airbus is lifting off at around 280 kilometers per hour.
The team discovers that the air that wraps around the top half of the car arrives at the intakes with 95% of its pressure intact.
It gets sucked and dives into the air intake here, leading directly down into the engine compartment.
The technical insight leads to a distinctive design solution.
It's one of those sort of eureka moments when you realize that the technical necessities are actually driving you towards a design solution that is unique. It's almost like there's certain inevitability in this kind of design.
This is probably the best indication and illustration where you can see form following performance at work.
Once the team solves how to get the cleanest air into the car, they face the next critical task: how to take it away once the engine is done with it. The quest to pull air out of the engine compartment leads to the striking cut-off rear end.
Weil wir haben eigentlich gefunden im Windkanal, dass wir nur durch das untere Drittel vom Stoßfänger, wenn wir da Druck ablassen und in die Seite reinpusten durch das Radhaus, das reicht eigentlich schon als der Effekt, den wir suchen.
Und gibt es sowas Ähnliches auch für hinten eigentlich?
Naja, wir haben ja so eine Art Venturi-Effekt.
The cut-off rear end is conceptually similar to placing your thumb over the end of a garden hose when the water's turned on. As the surface area decreases, the pressure increases, while also creating a vacuum in the remaining water supply. The back end of the car works the same way.
It creates a sub-pressure zone directly behind it for 1.5 meters, and it sucks out all the hot air from this whole engine compartment here.
Channeling air around the 1,500 horsepower engine is just the start when you're trying to build the fastest production car in the world. You've also got to cool something more than twice as powerful. The Cheron's 16-cylinder power plant generates 1,500 horsepower and pushes the machine to a planned top speed well over 400 kph. Yet going fast is just half the battle.
If you want to stop the car out of 400, you need 4,000 horsepower. So that means this thermal energy you have to get out of the car somehow.
To cool the car's brakes, the team literally attacks the problem head-on.
We have an integrated brake cooling air duct in the headlamp, which leads high-pressure air directly onto the brake.
Like the Veyron, the Cheron combines mechanical brakes at each wheel with an air brake at the back.
If you start braking from 400 with this air brake and the mechanic brake, you can have a deceleration up to almost 2G.
2G, or twice the force of gravity, is impressive. Yet the power of the mechanical brake is even more surprising.
The new brake is 3 times more powerful than the engine.
All that power is tested inside of a brake dyno.
Gibt's was Neues auf der Reifenseite von Michelin?
Von Michelin haben wir die Tests gefahren. Wir fahren mittlerweile die Reifentests auf dem Dynamometer.
When you're blazing a new high-performance trail, a big engine and powerful brakes aren't enough. You've also got to develop a new set of rubber.
We said it's gonna happen, but I don't know how today.
Michelin starts designing a new tire at their state-of-the-art facility in Clermont-Ferrand, France. The massive proving ground houses a high-speed circuit, a one-of-a-kind wet track, and enough pavement to make a tire shriek in terror.
For serious tires where you have, let me say, the guarantee you have lifetime, including traction and high-speed conditions on a long distance.
With just months to go before production starts, the guarantee is so critical that it needs to be written an ocean away. Inside Michelin's Aircraft Tire Test Center in Charlotte, North Carolina.
It's a very secret facility. It's the only facility to have tests in this extreme range far beyond 400 kph. We're talking about beating our own speed record, so we have more force on the tires at this very high speed.
Above 430 kilometers per hour, a tire will experience over 3,000 times the force of gravity just inside its air valve.
Michelin used to design tires for racing, like 24 hours of Le Mans.
Le Mans racing cars top out at around 340 kilometers per hour. The new Cheron will be over 25% faster.
It's why we have to go here in this facility, because the machine that we use to validate the tires for Le Mans cannot run that fast.
We have computer models and they show what we can do at this very high speed areas, but there's no experience because we are the first who are doing this.
Calibrating the digital realm with the real one comes down to one of the most powerful tire dynos in the world.
We are not far away from start of production. I could see that the tire is really capable to go for this speed. This is very confident for me.
As the start of production looms, the brand's future success on the track might very well hinge on a combination of science and nature. After nearly a decade of deliberation, Bugatti has finally chosen a path for their new supercar. They've built and tested a 1,500 horsepower motor, designed an exterior shape with optimal airflow, and engineered new brakes and tires. Yet the race to the finish line has just begun.
This is an outstanding challenge that you need to cope with every day when you work. For us, there is no room to fail.
Now the clock is counting down towards the delivery of the first machine, and the pressure keeps increasing.
Nothing is more important as this. In the past, we had sometimes colleagues, they forgot the birthdays of the children.
To succeed, the team must merge the artistic exterior shape with the technical requirements needed underneath.
So the process starts that we have a styling idea for the car and we have a technical vision.
Style and tech collide back inside Dallara Automobili, where they use a very earthly material to design a cutting-edge carbon fiber monocoque.
As you can see here, we are a lot of engineers developing the monocoque.
A monocoque is an automotive design technique where the exterior shell of the vehicle provides structural support. The process begins by merging the design department's 3D computer model with the lessons learned inside the wind tunnel.
We focus on CAD, creating 3D geometries. We make simulation through FEA.
FEA, or Finite Element Analysis, is a computer tool that simulates real-world forces.
So here we are evaluating all what is related to stiffness, safety and strength of the structural chassis.
The evaluation starts on an individual screen, but soon moves to a highly advanced virtual driving simulator, where a pilot can test the car before it's ever been built. Collectively, the team does over 100,000 simulations.
We are achieving really very strong numbers in terms of stiffness. We are speaking regarding a car that is more than 50,000 Newton-meter degree.
A vehicle with 50,000 Newton-meter degrees of stiffness is so strong that if you placed two average minivans on top of the left front wheel, the right rear wheel would only go up by 1 degree. The fundamental idea behind the machine's stiffness isn't new tech, but rather nature. The architecture that the team uses is similar to honeycomb.
You have one skin of carbon, honeycomb, and then another skin of carbon. This is called sandwich structure that is typically from aerospace.
Inside an aerospace-grade clean room, 50 artisans handcraft the honeycomb structure, where it takes 150 layers and over 1,500 hours to assemble a single monocoque. The process begins by layering carbon fiber sheets in a mold, before curing the unit inside an autoclave that bakes the monocoque at 135 degrees Celsius for over 15 hours. Once the unit is cured, it's moved into a climate-controlled, state-of-the-art milling machine, where it will take an additional day to remove excess material. Then they take yet another day and a half to scan the entire monocoque with an advanced laser to ensure that the chassis is dimensionally accurate. The finished monocoque weighs just 100 kilograms, and if all the carbon fibers were laid end to end, they would stretch from the Earth to the Moon 9 times. Time continues to tick as Bugatti engineers race to wrap up the development work on their first new machine in over a decade. Now it's time to step it up a notch and run the entire vehicle on a chassis dyno.
We need to do testing before road testing. That means test rig testing. This rig could show all the forces and torques which are coming to each wheel, moving the complete car on the test rig.
A 3.5-week run simulates nearly a year on the road.
It's also the first improvement of the durability and to check really is the stiffness as simulated.
Few people know the new Chiron inside and out, quite like chief engineer Willy Netteschil.
I could believe it. I really have to say, because for each engineer, it's a dream. Nobody thinks really it's possible that you can get such a job.
Amazingly, Netteschil's gift for engineering doesn't start at the track, but rather in the dirt. He leads VW's pickup truck project.
In former times, after my study for mechanical engineering, I started for trucks.
Netteschil and his team take prototypes for their first major public voyage across the Alps. It looks like fun, but is in fact a valuable tool for defining how far the project has come and how far it still has to go.
I do a self-test now and then to evaluate the car yourself, to feel the reaction the car shows and what is the area where we still might need to improve.
Next, the team takes the prototype to the famed Nardo circuit in Italy. Built in 1975, the course offers a unique 12.5-kilometer banked circle that's so large you can see it from space.
In this Nardo drive, I remember that we felt some reactions on the rear axle that I in particular didn't like too much. Als wir das letzte Mal in Nardo waren, haben wir ja an der Hinterachsabstimmung nochmal bestimmte Änderungen vorgenommen. Das haben die Herrschaften jetzt hier verbaut. Genau. Funktioniert das auch im High-Speed-Mode?
Every testing cycle, every couple of weeks, I'm holding my breath that nothing major will surface that will have us going back to the drawing board, because that would be pretty much a disaster right now.
Preventing disasters doesn't just happen on a track. While some prototypes are built to be run hard, others are manufactured to ensure perfection. Welcome to IndyCar, a master at high-quality artisanal small batch production. Here, the Chiron's interior is painstakingly put together. The craftsperson assembles an individual panel. Next, they install the piece on a precise modeling buck to ensure a perfect fit. Finished interiors are shipped nearly 550 kilometers to Molsheim, France. There are just a few weeks left, and the Bugatti atelier is in full swing, building the final prototypes.
Last step before start of production. Everything is assembled by hand. You have no robots in the atelier, only people. We are assembling the car in a box, like in a Formula One.
It takes 3 craftspeople to slide the motor into place. And just 14 bolts connect the rear chassis to the occupant cell.
When you produce a car who have a speed limit over 400 kilometers, every single process is critical.
After 1 week, a new machine is ready for its first run on a road. A rolling road.
We are making here all the road tests to make the running in of the brakes, for example.
Next, they install the curved sides, which are the largest carbon fiber body panels in the automotive world. Then the doors go on. Front quarter panels. And rear engine cover. The level of detail is nearly unmatched. Once the exterior is in place, they're ready to fit the handcrafted interior elements. When you're building a €2.4 million machine, authenticity is the key. Finished prototypes head directly to one of the most unusual testing facilities in the world. And the only place on Earth where the team can push the edge of the high-performance envelope. Welcome to Era-les-Cygnes, one of the most advanced and secure automotive test sites in the world. This is where the cheron will either get its stamp of approval for the start of production or send engineers back to the drawing board.
Era-les-Cygnes is my office, our office, yeah?
Era is holy ground for high-performance automobiles. This is the only place on Earth where car brands can push their machines safely towards the 450 km/h barrier.
What is special here in Era is really to have the top speed area.
Engineering is often a marathon-like battle of measured steps. Before the team can go flat out for the world record, they need to incrementally prove the machine. Today, the goal is to cross the 400 km barrier for the very first time.
This test now is really the final one for our team, where we approve really it's possible or not.
With the clock counting down towards production, the team can't afford any setbacks.
High-speed stability tests, because now we drive to 400 kph. And for this, we have to go very on the safety side, step by step.
Small changes can have a big effect on the track. After a few laps, Loris returns to the pits. He can't cross 400 kph because the rear wing isn't deploying correctly. And if the team can't get the job done, serial production can't begin.
I was telling them that I was doing some strange maneuver up on this banking.
Before Loris leaves the pits, the team reworks the deployment control software.
Try again.
Try. Should I start the engine?
Yeah.
We're just checking the situation if the wing is okay, in a good shape. So that means, as an engineer, I'm still concerned that everything is working in a perfect way.
A few laps later, Loris gives it another go.
A fast lap in the cheron is a really fast lap. The world is flying when you are in the car. above 400 km per hour, everything needs to work out according to plan.
It's taken Bugatti over 200 sets of tires, 5,500 laps at Era, and over 100,000 kilometers of testing to get to this point. Now, all they have to do is successfully drive past 400 kph so that the engineering team can give the green light for production to begin.
You don't do it just in between two appointments during the day.
Near max velocity, the cheron covers over 120 meters per second. That's nearly the wingspan of two 747s every second. Years of engineering succeed when Loris eclipses 400 kph. His exact speed remains a trade secret, but it's fast enough for the engineers to give the go-ahead for production to begin.
We work very, very strong to improve each small detail. And now you can see, here, have you a look on this? It's such but the feedback is very, very good from the driver.
After years of late nights and hard days, the team has achieved the first step in their quest. They can finally deliver the very first all-new Bugatti in over a decade.
It was really a big challenge, a lot of stress, a lot of problems what we had to solve. If you have a very big stone on your shoulder and you can say, oh, now I'm really on the top. How I achieved it.
I always used to joke, my colleagues are doing 10 cars in a year and I do 1 car in 10 years. But it paid off, and I'm so happy that it's sitting here today.
The machine is now built, but the brand's date with high-performance destiny remains. Only time will tell if Bugatti can best their very own world record for the fastest production supercar ever made.
I'm thinking often about this record, but I'm confident that we can do it. We know that we are on the border of physics.
Since the early 21st century, Bugatti has been the benchmark for sheer power and raw speed in the automotive realm. Their newest machine aims to go even faster and push the boundaries even further out of reach.
We wanted to demonstrate the world how fast you can go in a road-legal car. And we are ready to challenge the rest of the automotive world to beat us. And there are some guys around that already tried it. We really enjoy the competition. It's like in racing. Racing alone is not that fun, but if you have some guys that give you a hard challenge, then life becomes interesting.
The Bugatti Chiron. A handcrafted masterpiece, an engineering marvel, and perhaps the zenith of the combustion engine era of the automobile.